Thank you, Jack. Good morning. It's a great opportunity to be here. It's very nice after so many years to see some of the, to recognize some of the faces. The subject of my talk today, I challenge myself to try to bring a subject to your attention that I think it may be a little bit of a niche that is growing extremely fast, which is the use of high-performance computing in the context of analytical devices, analytical chemistry, analytical biology, and whatnot. So I will try to introduce this through a couple of examples. Analytical instruments are basically relatively inexpensive piece of hardware. We're talking about instruments that are typically below $150,000 or so, and are commonplace in pretty much every wet lab around the world. Actually, when I start putting together a list, their primary use in biological biomechanics, their primary use everywhere. And that is what makes this a very interesting market. Now, these instruments are actually, whoa, was that me? These instruments actually are finding new modalities of use, and they are the consequence of few unconnected events, including new forms of data acquisition. You have seen this in the more expensive instruments for the past 20 years. You're seeing the same cycle now for the less expensive instruments. You have seen this multiple times. Essentially, any instrumentation that piggyback on the multiple Moore law of the retinas, being that infrared cameras, visible cameras, UV, what you name it, transform the instrumentation very, very quickly. Now, the market for analytical instruments are roughly $24 billion. And this is a tricky number to estimate because traditionally this number has been, until about 2-3 years ago, estimated in the rough order of $10 to $12 billion. The jump is because you see instruments that were not originally cataloged as analytical instruments that enter into this area, like electron microscopes. We have 7 companies now that build electron microscopes for below $150,000. So even the evaluation of the market is kind of tricky. So let me conceptually introduce you to the problem of the evolution in a historical sense. I think this is necessary to really comprehend what is really going on. So what is an analytical instrument? Well, the typical analytical instrument in a wet lab is a microscope. Is the most trivial one you can think of. And historically, if you think about early uses, Ramon y Cachau was one of the early users. That's a vintage 1900 microscopes. He was using his eye for data acquisition. It's a camera. And actually, he was rendering what he saw by hand. So this is the beginning of the process. As a consequence of what he got the Nobel Prize of Physiology and Medicine in 1906. This is the fellow that actually uncovered the internal structure of the brain, still the morphology that we explore these days. Now, you jump forward, and you have Fritz Zernike. He modified the instrument. This is hardware modification. Still, data acquisition is nowhere to be seen. Instead of acquiring the amplitudes of the image directly, he is acquiring something similar to a self-interference pattern. We call it phase contrast. And he got the Nobel Prize in 1953. And you jump forward, and you recognize the pattern now. Betzig, Moeller, and Held actually developed what we know now as super-resolution microscopy. And here you notice a change. It's the same microscope, but it has a computer. Now, the way this actually emerged it's a very interesting story in itself. I don't have enough time to describe the whole process right now. But in essence, what happened is that through the algorithmic decomposition of the image, we can pierce what has been the diffraction limit of the image. So this is a biological sample. This is what you see with super resolution microscopy. This is you will see with one of the older microscopes. So it's a qualitative change that we went through in there. And of course, they got the Nobel Prize. So basically, get a microscope Now, this trend is accelerating. And if you think about describe, the first two techniques represent about 100 years in microscopy. What I described last, really the first idea was enunciated in 1978, but the first super-resolution microscope is from 1996. So the computational approach is still frozen in 1996 for a practical purpose. What is happening now is an evolution from that concept further. Again, for emphasis, with the old microscopy, direct data acquisition, super-resolution is the computer, the instrument. What we are seeing now is a breadth of new technologies. All of them look very similar. Low-voltage electron microscopy, nanoparticle tracking analysis, hyperspectral method. There are about 15 different companies that produce objects that look pretty much the same. It's an optical instrument with some advanced data acquisition modality and some type of source that depends on the instrument that you're using. What is different with these instruments is that they are starting to shift in the direction of connecting not just the instrument to the computer and output, but the instrument to the computer to the cloud to output. That messes up everything and start adding a fair amount of complexity in the way in which we operate with the data. This, by the way, is a hyperspectral image of rat heart tissue, I'm pretty sure, where you can differentiate between different chemical components through a single data acquisition. So what is happening now as an evolution of this is post-2005, is that we are seeing another change, which is the return from the computer to the instrument, where it's actually the computer the one that controls the instrument. Now, this is really quite complex a task, because, as I said from the beginning, these instruments actually are acquiring large amounts of data very quickly. So what you have to do is to model, simulate, or decompose the data quickly enough that you can actually inform the instrument that what you're doing is right or wrong, and modify your data acquisition on the fly, which brings back, basically, a lot of computational needs. Just for the purpose of example, let me show you one data acquisition we did ourselves. This is a nanoparticle tracking device. So the device basically is tracking single nanoparticles by a simple trick, very, very simple trick. This is a laser shining through a solution of nanoparticles. Every particle shines a separate speck against a very dark background. And you can collect these images typically for a material for periods of about 5 to 10 minutes. Okay? These are cameras with typical resolution of about 5,000 pixels in diagonal at 200 frames per second. So it's relatively high throughput. What is really interesting is the quality of information that you can extract out of this exercise. If you focus on one particle, you can do several things with this. You can actually track the particle as it shivers, as it moves around its average position, and that gives you information about its size. So the radii, what is called the hydrodynamic radii, came out of that calculation. That you can do in your cell phone is fine. It's a relatively simple thing, at least for one particle. And when you want to do it for a couple thousand particles, things get a little bit more demanding. What is really interesting, though, is that with the same instrument, you can track the flickering of the particle. If you remember what you saw in the movie, the particles actually blink. They move very rapidly. Now, in that flickering of that, in that signal, is information about the shape of the particle that you want to recover. Now, for that, you cannot saturate your camera, so you will have to do this with probably 2 or 3 cameras in parallel in something like an HDR-type movie, which triple the flow of information that now you're acquiring. Now, the way you process that information is somewhat similar for those of you that are familiar with Shazam. I mean, I don't know how many of you sing in your shower, but if you sing to Shazam, it will guess what is the song that you're singing. Not for me, but for those that know how to sing. Now, the advantage for Shazam is that songs have an internal periodicity. They're really simple to process. These signals do not have any of that. So it's like building a Shazam where what you're trying to get is not the title of the song, but the style of the composition. So you really need a lot more information, a lot more volume of information. Okay? Now, we don't have that. And we have some demands as we process this information. The system is a capillary, and it can get dirty very quickly, very easily. So one of the things that you need to know is if what you are capturing during those 10 minutes is the same thing. So what you're going to do is a self-similarity analysis using that frequency spectrum that I mentioned before, over hundreds of thousands of frames on multiple cameras. If things don't work the way you expect, you need to change the conditions in the instrument so that you can change the conditions for data acquisition. And this is an emerging bottleneck across analytical techniques. So I will emphasize this again and again. You can capture petabytes of junk, or you can have active computing guiding the data acquisition to capture meaningful information, which is a real challenge. Now, as I mentioned before, mine is an issue here as well, because the platforms are rather inexpensive. For $10,000, you can get your own laser and play at home with it. So there is a need for coupling this in what Jack called the local HPC type of environment. This is the type of infrastructure that will not necessarily expand on its own capital base a whole enterprise. It's a completely different dynamic in terms of a market. What you have here is volume. You have tens of thousands of these instruments worldwide. Okay, just for emphasis, 9, yes. I can show you another example. This is probably a little bit more familiar in the way we operate. This is an electron microscope. And again, it's not what you envision as an electron microscope, because it's an optical microscope with an inverted electron microscope where the electrons are running bottom up. Once again, this is finding its way in a number of markets as an analytical instrument. Now, when you acquire images with this microscope, you have all the type of troubles that you have seen in the past with other electron microscopies, and probably you have seen similar images before. The particles drift. The particle here is that donut. The particle drift. There are changes in contrast, and you need to clean all of that before you can do something with that information. I'm running it again just to emphasize one point. If you notice how much the particle drift and how much is coming in and out of focus, what I'm doing during the data acquisition is I'm aiming to the middle. I'm hoping that I have my parameters during data acquisition set up properly. If I don't do anything, most probably I will be wasting 90% of what I'm doing, because the support for the samples, this is approximately 5 minutes exposure. Those little white dots that you see in there is getting damaged. In this particular case, the support was sensitive to radiation and was getting damaged. So the only way to get the full potential for this method consists in extracting information and trying to figure out whether the parameters that I'm using for data acquisition are correct while I'm acquiring that information, which again is really quite demanding. Just to give you a sense of what quality of problems we're dealing with here. This is one raw image, just for this instrument, roughly speaking, on the field of view, you may get something in the order of 500 to 10,000 of these images. So for each of them, you're going to try the following analysis. You're going to look through the stack, that's the pair average, and you're going to try to find out the noise image, the associated image that reports the noise on the image that you're capturing. If this noise actually is constant and large, you're either out of focus or you're capturing your information wrong. And you can acquire petabytes or exabytes, and it's going to be exabytes of junk. So the point here is to process as you go to try to improve the data acquisition. Once again, the emphasis here is in a model that is changing rapidly in analytical devices from what was once direct acquisition, end product, and then you can process, batch processing at the end of the data acquisition, to a mode of operation in which we will have to understand the data as we're collecting the data as rapidly as possible to change the parameters for data acquisition. The same logic impacts other fields and other initiatives that you probably have heard about. The free electron lasers is one particular example that I think has been reviewed quite a bit in the literature. By the way, this is from a review in Nature, I think it's September 2014, of free electron lasers. And the problem basically is the same at a much larger scale, but ultimately is the same. What we are doing in the free electron lasers is collecting, rather blindfolded, a very large number of exposures of materials. Remember, these are guns that actually destroy the sample during data acquisition. So you acquire very, very quickly, and then you think. And that doesn't work terribly well. I mean, it's great during the stage of development because you're just trying to find your way, but this is not, it's not the optimal way of doing it. Now, there are some limited similarities to problems in other areas, but they are limited. They are really not exactly the same in nature. Weather forecasting is one example where you need to react. If you're tracking a vortex and you're trying to figure out what is going to be half an hour from now, you need to process massive amounts of information. However, you're not going to change the position of the cloud. You're not going back. The problem here is that you go back to the instrument and introduce changes in the instrument. So again, there are examples, you're familiar with them, but they are not exact in nature when compared with analytical instruments. As I said from the beginning, this is not a massive field right now. By my estimate, probably of this new generation of instruments, there may have been something in the order of 5,000 deployed, and is a very fast emerging market. So I think it's something that for those that are interested may serve as an interesting point for conversation. And I thank you for that.